Thank you all for coming. It's a pleasure to be talking here. Thanks for coming after the lunch. I'll make sure you don't fall asleep with lots of math. Even the title is a bit cryptic, so it will be a surprise what it's about. So let me start by introducing myself. My name is Alp Bassa. I'm head of cryptography at Veridise. So Veridise is a security company. We do audits in the blockchain space, focusing a lot on ZK, but also other stuff too. And most of the team members come from academic background, more on formal verification. So we also have some in-house tools that we develop that we use in our audits and so on. And we also have some research that we do in-house. And it's a lot about formal verification, but we also do research in cryptography and number theory and so on. So today I'm going to talk a bit about cyclic groups from geometry. So what's it about? So, you know, lately there have been all these variations of the fast Fourier transform. You might have heard ECFFT, circle FFT, Galois FFT, and so on. And I'll not talk about anything new, but what I'll try to do is I'll try to give you a way of think of these in a unified manner. There are very many nice ideas in all of these contributions. Maybe one aim of the talk is to push them more into the spotlight, and I'll try to kind of show how you can kind of interpret many of the results there from results about curves, covers of curves, automorphisms of curves, and some basic group theory. And I don't claim to be complete. There are many details I will leave out, but that's just to give you a rough overview how you can kind of see them together as instantiations of one idea, and that will hopefully help to generalize it and kind of hopefully boost some research in this direction and cause some visibility to those nice results. Okay, so first about FFT, I guess most of you are familiar with. So the main idea is that when you have a polynomial, let's say over a field, in our case it will be a finite field, there are various ways of representing it. One way would be to just list all the coefficients, but you also know that if you have a polynomial of degree n, it has n plus 1 coefficients, and it is uniquely determined by its value at n plus 1 points. Yeah? So these n plus 1 points, x0 up to xn, I will call the evaluation domain. And rather than thinking of the polynomial as represented by its coefficients, you can think of it as represented by its values at those points in the evaluation domain. Yeah? So you can pass back and forth between those two. I mean, because of some analogy with like the Fourier transform, you can usually call the coefficient form the time domain, the values you will call the frequency domain, and you want to kind of pass back and forth. And this is basically just linear algebra. Yeah? So you have the vector space of polynomials. You can either represent it in a monomial basis or a Lagrange basis, and that would just correspond to passing from the coefficient form to the evaluation form. Yeah? And why is that useful? I mean, for instance, if you want to do fast polynomial multiplication, if you have two polynomials of degree n, if you want to multiply them in a trivial way, you would need order of n squared operations. If you do it a bit better, use Karatsuba or something else, you can lower that. But if you represent your polynomials in evaluation form, then you know that the value of the product of two polynomials is the product of the values of the polynomials. So you just need to do a component-wise multiplication. Yeah? So you can pass from one domain, multiply there fast, and then pass back. Of course, there's the issue with the degrees of the polynomial, so I'm not going into any of those details, but this would be just one reason why you would be interested in having polynomials represented in evaluation form. And to pass from one representation to the other, basically what you would need to do is you need to evaluate the polynomial at many points, so you need to do fast multi-point evaluation. Given a polynomial, you want to have a fast way to evaluate it at many points. And the fast Fourier transform allows you to do it in n log n, order of n log n operations. Yeah? So how does it work? So let me talk about the more general. Set up the discrete Fourier transform over a finite field. So you have a finite field with q elements. You take a primitive nth root of unity. So this requires that already there is an element of order n in the multiplicative group of the finite field. So n has to divide q minus 1. This restriction will be important later on in the talk. And you just take as your evaluation domain the nth roots of unity. Right? And then when you want to evaluate a polynomial, you just have to compute that sum over there, which is, in fact, in terms of linear algebra, it is just a multiplication by a van der Monte determinant, which already shows that also going back will be something similar, right? Because the inverse of a van der Monte determinant up to scale is, again, a van der Monte determinant. Okay, so how can this help speeding up? So assume now that the n that you have, that was the order of the root of unity that I had. So n was the size of the evaluation domain. Suppose n is a power of 2. Yeah, so you need that a big power of 2 divides q minus 1. You again take a nth root of unity. You look at all the nth roots, and you look at that as an evaluation domain. But then some very nice idea is basically if you want your polynomial, if you have your polynomial f of x, you can separate it into those monomials that have an even exponent and those that have an odd exponent. So given f of x, you can write it in this very particular form using polynomials f0 and f1 of half the degree. How is that useful? It's useful because of the following fact. If you have a root of unity of order 2 to the L, its square will be a root of unity of order 2 to the L minus 1. So evaluating f0 of x squared or f1 at x squared as at any of the roots of unities just corresponds to evaluating f0 or f1 at the corresponding 2 to the L minus first root of unity. Yeah? So basically, the squaring operation that you have shrinks your evaluation domain. Yeah? So the evaluation domain shrinks, the degrees of the polynomial shrink, but the number of the polynomials double. Yeah? So rather than evaluating one polynomial at 2 to the k points, you will evaluate two polynomials of half the degree of 2 to the k minus 1 at half the many points. Yeah? And you can you don't stop here, you can go on recursively rather than evaluating f0 and f1 at the smaller evaluation domain that I'll denote by s1. You can again separate them, both of them, into odd and even parts and go on like this. Yeah? So you might be wondering what's going on here. If you want to generalize it, understand it, like there are some very nice things that fit in very nicely together. Right? You have the set S, the evaluation domain. You have the map x squared, right? That was kind of the map that you have substituted into the polynomials. There's this one function x in front, and they fit very nicely together in the sense that if you take your evaluation domain, if you square all elements, the size gets half, right? And you know that for given a polynomial of the given degree, you reduce the problem to polynomials of lower degree. So there's lots of magic happening here. So once you understand this magic, you can try to understand, to kind of generalize it and mimic it in other setups, right? But in this particular case, we needed that q minus 1 is divisible by a very high power of 2, or that it is at least a smooth number. It has many small factors. And this puts restriction on the q that you can use, on the size of the finite field. So it puts restrictions on the finite field itself. Yeah? So you might want to use some other primes that are good for fast arithmetic, like Goldilocks primes or Baby Bear and others. But they do not have this property that q minus 1 is divisible by a high power of 2. Oh, sorry. They do have, you can find those primes that have this nice property that q minus 1 is divisible by a high power of 2, but you have to restrict to those, basically. You have to look explicitly for primes so that p minus 1 is highly divisible by 2, which kind of is a restriction that you want to get rid of. Yeah? And a solution to this is to look at variations of the fast Fourier transform. One way would be, rather than looking at 2 to the Lth root of unities, you can generalize it at 3 to the Lth root of unities. So you want that p minus 1 is divisible by a high power of 3. Or there is another method called the discrete Galois transform by Crandall from 1996. So it says that if p plus 1 is divisible by a high power of 2, so if you take a prime p such that p plus 1, not p minus 1, but p plus 1 is divisible by a high power of 2, you could, for instance, take any of the Mersenne primes, then, if p plus 1, this would imply that p is congruent to 3 modulo 4, right? If your power of 2 is at least 4, you know that p plus 1 is divisible by 4, so p has to be congruent to 3 modulo 4. You know that minus 1 does not have a square root inside fp, so there's no element whose square is 1. You can adjoin that element that I just denoted by I. So it's an element whose square is equal to minus 1. You can adjoin it to fp, you get an extension field, fp squared. And then the nice thing about fp squared is it's just like the Gaussian integers, so it's elements of the form a plus bi, where a and b are in fp. So you have a total of p squared many points. If you look at the invertible ones, you get p squared minus 1 points, right? So in the normal finite field, the multiplicative group had order p minus 1. Now we have a multiplicative group of order p squared minus 1. But for that, we paid that we have to work in a larger finite field, right? But the nice thing is p squared minus 1 has not only the factor p minus 1, but also the factor p plus 1. Yeah? So it would help you if already p plus 1 is divisible by a high power of 2. And in the particular case of a Mersenne prime, if you take a prime of the form 2 to the q minus 1, you see you'll get a total of q plus 1 factors of 2. Yeah? And, but for that, what you pay is you work inside an extension field. You have to weigh out if it's worth or not. And this idea, I'll come back to it later when I talk a bit more about circle STARKs. But there are some nice results also already for those fields. So if you take a Mersenne prime, other than the case where q is equal to 2, then a result by Kreuzburg and Tesche already tells you how you can explicitly find a primitive root of unity, right? And it also helps that although you're working inside fp squared, your initial problem was something in fp, so you wanted to evaluate at points in fp, so it's kind of a way to say that you do like a Fourier transform with real signals, so to say. You can create some speed up from there too. But then the question is, what are other options, and can we really understand what's going here behind the scenes? And for that, I'll talk a bit about geometry. Yeah? So we had seen that in the fast Fourier transform, this map x squared had played a prominent role. So let's look at this squaring map. On the left, you see the graph of the squaring map in the case of complex numbers. Basically, you should think of the complex plane, and then for each complex number, you have 2 square roots, right? So over each point in the plane, you will have 2 points lying, 2 points on this of the surface that lie over each point, except the point 0 will only have 1 point lying over it. Or you can visualize it in terms of the real picture. So if this is the y-axis and that the x-axis, x squared is equal to y. So for each y value, you have 2 x values that map to the given y value. Yeah? So basically what you have is, I'll just tilt the picture over. So you have a 2-to-1 map from the graph, the parabola. You'll have a map to the y-axis, right? And for each point on the y-axis, you will have 2 points on the curve mapping to that 1 point. Yeah? Or if you want, let's move the y-axis out. So you have the parabola over here, you have the line down here, and you have a map from the parabola down to the line. That's the squaring map, right? Such that for each point on the line, you exactly have 2 inverse images, except the 1.0, which has a point of multiplicity 2 over it, if you want. Yeah? Okay, and you can think of this more generally. You can have a complicated curve, and it could cover a simpler curve. If you have a map from a higher curve to a lower curve, this is called the covering. And given a point P, it will have 3 points, Q1, Q2, Q3 over it. But if you take another point R, it might be that one of the points might come with a multiplicity. Yeah? So if you take the point P, move it slowly towards R, you see that the Q2 and Q3, those 2 points will collapse to a single point, S2. So you should think of S2 as a point with multiplicity lying over it. But counting with multiplicity, if you have a certain covering map of a certain degree, you will have as many inverse images as that degree. Okay, and now in the fast Fourier transform, you're basically repeating the squaring map many, many times. Yeah? So basically what you're doing is you have a line, you have the squaring map down to another line, that's a 2-to-1 map. Any point on this second line will have two inverse images. You apply the squaring map again, again, and again. Yeah? And you see already if you take a certain set, it looks like if the set is chosen nicely, it will shrink. Yeah? But then the problem is, of course, I mean, as you know, in the world of real numbers, if you want to take a square root of a number, the outcome might not be real again, right? If I take the square root of -1, I get a complex number. Yeah? So you might have to grow the field, and that you don't want to do. So basically, you want to have points up there that are defined already over the field over which you're working, such that under the squaring map, you get to smaller and smaller sets. Yeah? And the way to kind of ensure this is using automorphisms. So basically what you do is on the line, you have an automorphism of the line to itself, which corresponds to taking a point, multiplying it with the root of unity, right? And then if you take a point and if you look at all of its orbits, right, when you pass to the quotient curve, that orbit will collapse to a single point. Yeah? Except the point 0, that will be a fixed point under that group action that will have, so it will be a single point lying over a point down here, right? So basically you see, you obtain in a very natural way from an automorphism of the curve up there, you get a quotient map to a curve down there, which just has a point down there for each orbit up there, yeah? So whenever you have a curve with a group acting on it, you can kind of quotient out that group action, you get a curve down there. Okay, and then we had this nice property that if you have a function f, I could write it in terms of two functions, f0 and f1. This is basically related to a way of connecting functions on the curve up there and functions on the curve down here once you have a covering map. If I have a function f on the lower curve, then I can pull it back to a function up there. Basically, if I know how to evaluate a given function at points on C, if I have a map phi from C prime to C, I can obtain a new function, phi star of f, which is taking a point. If you want to evaluate phi star of f at that point, you just first map it down, and then you map by f. Yeah? So it's basically just composition with phi. And in our previous case, phi was x squared. And if you remember, we had f0 of x squared and f1 of x squared. That's just composing with the covering map between those two lines. Yeah, exactly. That's the squaring map. And here, basically the pullback of a given function was just composing it with the map phi, which gave you this function x squared over here. Okay, so we have seen that automorphisms and coverings, they're intimately related, and they might be useful. And we have seen that the function spaces are also related to each other, right? Given functions down, you can pull them up to functions above. And in fact, all functions above, so I'll denote by fq of c prime, all functions on the curve above. Fq of c will be the set of functions on the curve below. And you see easily that the functions on the curve above are forming a finite vector space over the field of all functions below, right? Which means if you choose a certain basis, you can write any function above in terms of functions below by multiplying by those basis elements. And in the case of the squaring map, that basis is just the basis 1x. So that's why that x factor in front of f1x squared was coming from. But of course, you don't want arbitrary functions. You want to restrict on to nice functions like polynomials and so on. And there is ways to do that, but there's some further reasoning that you need to do at this point. Okay, so maybe this was fast and a lot, but basically the upshot is if you have a curve, if you have automorphisms on the curve, you can get functions down to a simpler curve. Functions above you can write in terms of functions below. And the evaluation points, if they're chosen nicely, if they're chosen as orbits under that automorphism, they will always shrink in size. Yeah? And having automorphism will also guarantee that you have many points. Yeah? So that's kind of the rough idea. Okay, so then let's see what we can do with the line. Let's start with the line, and what can we map to from the line, right? So basically, you're interested in automorphisms of the line, and it's very classical. They are just the elements of the projective general linear group. Yeah? So given a point on the line, you can just apply this Möbius transformation, right? Given coordinates x, you take a matrix A, B, C, D with non-zero determinant. You can map x onto the by the Möbius transformation ax plus b divided by cx plus d to another point again on the line. And that gives you an automorphism of the line. Yeah? In fact, it's a projective line, but I'm not going to go into those details. Yeah? So you have this very large automorphism group of the line. I mean, the line is very simple, but it has lots of structure. It has a huge automorphism group. And then the idea is, okay, let's look at subgroups of it. The subgroups will define you the quotients. They will define you the maps phi. And so they will give you the covering. They will give you which functions to compose with. And they will also tell you what the nice sets are that you want to have. And also, if you want your functions to be invariant under those automorphisms, that will also be possible by looking at them. And then subgroups of PGL2 are classically known. I mean, it's a result by Dickson more than 100 years ago, which basically tells you over a finite field, the projective general linear group has only those subgroups. Yeah? And I just want to stress, like, the last ones are not too interesting. A4, S4, A5, they're just finite, so you can't do much. There is no parameter n that you can grow in it. We have the elementary abelian P groups. We have the cyclic groups of order dividing Q minus 1 and Q plus 1. That's already two factors we had seen before. And we have the dihedral groups. Yeah? So let's go one by one. From the elementary abelian P groups, you'd basically get what is known as the additive FFTs. If you look at the cyclic subgroups of order dividing Q minus 1, this would just correspond to multiplication by nth root of unity. That would be the automorphism that you have. And that's the very classical construction, yeah, where you take nth roots of unity and do the discrete Fourier transform. And if a high power of 2 divides n, divides Q minus 1, you can choose that as n, and that will speed up things. Yeah? If you look at cyclic subgroups of order Q plus 1, so these are known as Singer subgroups. I mean, there is a construction, what their generators are, and so on. I won't go into those details, but you can easily construct elements in the automorphism group. So you can construct matrices of order Q plus 1. Yeah? And that's basically what's used in the Galois FFT by Li and Xing. Basically, they take just an element of order dividing Q plus 1 and use that to kind of shrink the evaluation domain and the function space that they're looking at. And then there are the dihedral groups. So dihedral groups just correspond to symmetries of a regular n-gon. Yeah, so there's a parameter n. If you have a regular n-gon, like a 6-gon, 8-gon, the stop sign, right, you can just rotate it. And what you can do is you can also flip it. Right? And the set of all those symmetries, they form the dihedral group of order 2n, and they just correspond to, if you look at the root of unities, they just correspond to rotating in the circle, yeah? Which brings us to the circle Stark, or the circle FFT, by Haböck, Levit, and Papini, which basically uses a model of the line given by a fine curve, which is the circle. Right? On the circle, you have an action of the algebraic group SO2, which is just the rotations, basically. It's a fancy way of saying rotations. And basically, a point would correspond to a certain rotation. If you have a point with coordinates CS, it would correspond to this matrix over here. And C and S are basically like, they should remind you of cosine and sine, which are the usual functions that you get when you do things in R2. And reflection along the x-axis would correspond to inversion. And what you can do is, so inside this dihedral group, you have, first of all, a cyclic group of order n. If you use that cyclic group, you would be getting back the Galois FFT. Alternatively, you can use the full dihedral group, but then you have some issues with ramification and so on. So I won't go into the details, but you can't use the whole dihedral group, but you just have to use half of it. And once you do that, you recover the circle FFT. So basically, these are, so to say, the maps of curves that you have. Either you can first take an inversion and then go down n-1 step, or you can just look at the cyclic subgroup and go down all the way here. Yeah? That's how they are kind of related. And the reduction step, I mean, basically you would be choosing a base on top. You have this field having x and y. Below, you have the field having x only. You can choose one y as a basis for the one above. And then afterwards, it's basically a squaring. It's not really a squaring, but it's so that the whole composition map corresponds to taking out quotients by dihedral groups. Yeah? OK, and then there's the ECFFT. I have no time to talk about it, but it's a very nice construction. Basically, what you do is you ask yourself, what are curves where I have a very natural group action on? And elliptic curves are a group by themselves. So you have a group action given by translation. So given an elliptic curve, you can take a subgroup, and then you can have a map from the elliptic curve to the quotient by the translation map, by the group generated by translations corresponding to points in the subgroup. Yeah? The problem is you have to work with bivariate functions in this case, because you have an x and a y coordinate, and you have to work with points with two coordinates, but in fact you don't. So that's, again, very classical mathematics beginning of the 20th century. Lattes map basically say that on the elliptic curve you have this involution mapping a point to its negative. If you quotient out by that, you get a map to the line, and this quotienting out by -1 behaves very nice. It commutes with all the isogenies. So if you have a nice map phi above, you can get a similarly nice map phi hat down there. Yeah? And this gives you the ECFFT construction by Ben-Sasson, Carmon, Kopparty, and Levit. And so I'll just finish with some questions. There are many questions that you could ask at this point, depending on what your taste is, what you're looking for. But basically, one first question would be, there are several models for all those covers that you have, right? There are various models for the groups. There are various models for the coverings of curves. And can you choose another one? What is a way to optimize it? Can you do this optimization for additive FFTs? The Riemann-Roch space, which is kind of the space of functions that you're restricted to, has a lot of algebraic structure besides being just a vector space. Right? It's basically functions, and you can not only add them, but you can also multiply them. Can you exploit this additional structure? Can you, rather than evaluating at points, can you evaluate at points in extension fields? What's the optimal way for ECFFT? What are good choices for elliptic curves and isogenies? Can you use other projections to the projective line besides quotienting out this involution multiplying by -1? And then there are a whole bunch of other curves of higher genus, not the line and elliptic curves, which are genus 0 and 1, but arbitrary high genera. So those curves have many more points. Can you use those? So you don't have to kind of restrict yourself to what's bounding you, namely the Hasse-Weil bound. You have very nice curves with many automorphism, many points. The Hermitian curve, Suzuki curve, recurve, might they give you anything? Yeah, this and many other questions, but I'll stop here and thank you.